Okay, so we're going back to the disk method. This is kind of a subset of the disk method called cross sections. So it doesn't involve revolutions. It involves building figures. And this will make a little more sense when I show you what it looks like. We're going to take a function, like for instance this teardrop function that we talked about, and stack, not stack, that's the wrong word. We're going to, yeah, stack I guess works. We're going to stack figures up on top of that and eventually make a shape. So the figure that you stack on top of this can be whatever you want. We'll look at rectangles, triangles, semicircles, all kinds of fun things like that. And again, this will make more sense. Oh yeah, so I only have one thing to do. Find the volume of cross sections. Okay, so boom, 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 boom. All right, let's go to Sketchpad. So you get an idea what this looks like. Yes, I know it'll not my computer. Okay, so here's what we're going to start with. We start with a base, and that base can be a lot of different things. That's where our function is going to come into play. In this case, I'm using a circle. It's not really a function, but my base will be some type of function, even though it's not a function. Roll with it. Okay, so I'm going to draw a bunch of chords in there. Then, I didn't want to do that one. I wanted to, we'll do it anyways. Okay, I'm going to take on top of that thing and sweep, hold on a second. Stop there. Let's do equilateral triangle, see if this one's working correctly. Show chords, drop. There we go. Okay, so I'm going for kind of a 3D thing going on there. You see what happened? Took the circle and tilted it down. I'm going to stack on top of that circle equilateral triangles. And so as they get very close to this one point, the equilateral triangles are going to shrink. And as they move away, they're going to get bigger. Okay, so it looks something like that. It starts there, and as they slide further out, the equilateral triangle gets larger. And then as it slides back down, it gets smaller. And of course, since this is calculus, we can use integrals to add up all those equilateral triangles. Okay? Eventually, it's going to look something like this.
So you put another half circle on top.
Yeah, it's fairly bizarre. And then here, I just showed that. There's the solid. Okay, so we can grab this. Can I rotate it? Yeah, there you go. So there it is in 2D, 3D. Wow, that was pretty cool.
Do it again.
Do it again? 2D, 3D. And then, let's see. Slide an equal triangle. So there's a solid, and you can see that triangle. So you can see we got two things we can change. What is it sitting on? In other words, what's the shape of the base? And what shape are we standing up on top of it? So I've got something like the square thing. Let's see if I can get this to work again. Excuse me. Why didn't, that's dropping down too far. Okay, so let's see if I take this. There we go. Let's move it over here. Now we got some 3D action going on there. There's some squares. Sweep one square would look like this. And then when you create the solid, you get that thing. I think I can slide that down. I'm not sure. Oh, there we go. Now we're in business. So that's pretty bizarre. Are you expected to be able to visualize those? No. If you can, there's something wrong with you. What you should be able to do, though, is calculate the volume. The math for this is really simple. It's the setup that's a little tricky. Okay, let me show you one more, and then we'll be done. So let's change the base. So we'll turn the base into a right triangle, not an isosceles triangle. But we'll stack on top of that semicircles. So get the 3D look going here. And then sweep one semicircle so you can see what that looks like. Very far away, it's going to have a wider radius, so a bigger semicircle. As it gets closer to the point, it shrinks down. And so we end up getting that thing. I'm sorry, a bugle?
Yeah.
As in a trumpet or as in the snacks that you put on your
Snacks.
fingers?
Snatch my fingers.
Which snacks?
I can't put them on my fingers anyway. I'm gonna be fat sausage fingers. That's kind of a pseudo cone looking thing there. Okay. And we can change, like I said, we can change just about anything. Semicircles on a triangle. What else have I got here? What's this guy? Oh, we don't want to go there.
Let's
go. No, let's go back.
Do it. Do it.
I don't
Okay.
want to go there.
It's not that. It's not that exciting. It's just a triangle with triangles on top. It makes a three-dimensional tetrahedron. The key. Ooh, what's that do? I don't even know what that means. Okay, so let's go back to the lesson and see how we do this now. No, I don't want to say. Thank you very much. Okay, so here's again some pictures. This is it. That's the formula. It's really simple. All we need to do is calculate the area of that shape standing up on top of it and integrate it to add up all those shapes. Now we may have to do a little bit of work to find that area, but it's still fairly reasonable. No pi, no 2 pi, unless of course you're dealing with a shape that has pi involved, like if we're standing semicircles up on there, then you might have a pi. But in general, it's just the area of the cross section integrated for all those cross sections. Okay, and it'll become a little bit more clear if you see some examples. All right, so we're going to start with this. Just for giggles, draw that. Just to make sure you know what you're doing. Forget about the cross-section stuff, just draw the first part. Region bounded by the graphs of x equals y squared and x equals 9. Okay, we good? What's x equals y squared look like? Not just the square root.
Plus or minus.
Yeah, it's the whole thing. So it's a parabola on its side. Parabola on its side, and then the line y or x equals 9 is going to cut it off here. Okay, this is the region. That's going to be our base of the figure. And then we're going to stand something up on that. And in this case, we're standing a rectangle. First time through, I made it a little bit easier because I fixed the height of the rectangle. If you go back and think about the one I did with the equilateral triangles, the height of that equilateral triangle changed as you slid through the figure because it's equilateral. This one I have the luxury of restricting my rectangle to be the same height. So try to visualize in your head what this is going to look like. Got it? What's it look like?
It's just taller.
Yeah, it's just a three-dimensional parabola. It's not real exciting. Okay? Again, we're starting easy before it gets kind of crazy. Okay, so here's the best way to keep yourself sane doing these problems. You'll see this big bold line here. Realistically speaking, you probably want to move this big bold line over here. Okay, because that's going to become our representative rectangle, even though we're not spinning it. What happens now with cross sections is that the representative rectangle becomes the base of your solid. So you'll notice I've got a big bolded line here. I've got a big bolded line down there. So when I build this figure, this rectangle would be sitting on this like that. And then we're going to sweep it from 0 to 9. The hard part is finding the area of that rectangle. And this one's not too bad. I picked some point on this function, and I got x times the square root of x. Does that make sense? X, f of x, yes? I picked a random point on the graph, x comma f, square root of x, which is x comma f of x. And we're dealing with a function, y squared is the same thing as, x equals y squared is the same thing. Okay.
Where are brownies?
The reason I'm late is my dog ate them. She's fine. But I just had to stay home.
Your dog ate a whole...
Yeah.
Oh my god, is she okay?
I just stayed home to make sure she was okay. She's fine.
All right, I'm gonna give you, that's a pretty good excuse.
Yeah.
We're gonna cut you some grief on that one.
Alright, yes.
But you're sure she's okay?
Yes. I mean, if she was like, if there's any harm, she'd probably like her heart would be racing. She'd like be freaking out when she's sleeping. So.
I understand. Remind me when I stop the recording, I'll tell you a dog story. I don't want to record it. Okay. So, do you see where I got 2 times the square root of x? This height is the square root of x, and it's double that distance, so I just doubled it. Okay. When you get to that point, the rest of this is cakewalk. What's the area of that rectangle? 4 root x. And I'm taking rectangles from where to where? 0 to 9. Done. Okay? Bingo. And for those of you that are playing, oh no, I don't have the answer, sorry. I was going to say for those of you that are playing at home, here's the answer, but I don't have the answer.
I have a question.
I thought that is the answer.
I think I missed it. How did you get the height to be 2?
It says in the problem, I'm fixing the height at 2.
Okay.
Where'd you get?
This distance, let's back up. This solid, this bolded segment matches the base of the rectangle.
I
So,
get it.
you got it? Okay. Everybody good? Yeah.
Does that bolded line have to be at 9?
No, it could be wherever you want. It's our representative rectangle. For some reason, I put it over there.
Okay.
Exactly. 70.000000035. That's what I said. She said exactly 70.9 Got it.
All right, let's try another one then. This one will get a little nastier. This one will be similar to the one I showed you in Sketchpad. We're going to start with a circle with a radius of 4, which hopefully you can visualize that in your head. And we are going to create a cross section with equilateral triangles perpendicular to the y-axis, on a base with a circle of radius 4. There we go. There's my circle radius 4. There's my equilateral triangle. So again, visualize that equilateral triangle sticking up out of the board at you. How are we doing so far? Okay, good. Now the fun begins. We need to find, so here's the function of the formula for a circle. You all knew that, right? X squared plus y squared equals 16, because the radius is 4, so okay, great. Which means that x is equal to the square root of 16 minus y squared. Why did I solve for x? Why not solve for y?
Because we're supposed to be doing it in terms of y because the representative rectangle is horizontal.
Rock solid. I'm not even going to comment. It was so well said. What you mean?
Why is it not plus or minus?
It could be,
Oh.
but all we care about is we just need
One
a
of the
distance.
sides.
Yeah. So it would be plus or minus if we were graphing the whole circle.
Okay, yeah.
But we just want to know where that point is.
Gotcha.
Okay. Okay, so far. Hot diggity. There's my triangle. So think about it this way. Where is that point located? That point is located at x comma f of x. But the problem is we're working in terms of y, so it's going to be kind of like an f of y comma y. So that point is at the square root of 16 minus y squared comma y, which makes the base of this triangle twice that distance from the y-axis to the point, just like we doubled the distance in the last example. Okay, we good? Now I'm sure from geometry you all remember the formula for an equilateral triangle. Cricket. No. Area is equal to, no, but for an equilateral triangle, S, squared times the you know, square root of 3 all over
3,
4,
5.
Good. I knew you guys would remember it.
Did we ever do that familiar?
No,
I never learned that. You should have learned that.
I really
Regan, you learned that. Just say yes, Regan.
Yes,
Good.
of course
See?
I did.
Lying to you.
She just didn't want to make anybody feel bad, so she didn't want to volunteer that information. It's very kind of you, Regan. Thank you. In that picture, what's S?
No idea.
2
root 16.
Good. S is the length of one side of the equilateral triangle. So we do a little plug and chug. And we're almost home. This is, yeah, you don't remember that. I didn't really expect you to remember that. But now that you know that, this is the hard part here, getting this, because if we know that, then we just take this and plug it in there. That's going to give us the formula for the area. And we're taking triangles from where to where? -4 to 4. Or you could go -4 to 0 times 2. Or 0 to 4 times 2, because it's symmetric. You with me? Yeah, whatever you want. So there's the area. That's kind of not a nice equation. But when you square it, it becomes a little bit nicer. And if you distribute, it becomes even nicer because the first term is a constant. Move it out in front of the, no, you can't, sorry. When you multiply, you get a constant, but integral of a constant is simple. Oh wait, sorry, I went really quick there. That's the wrong button. Are you okay? Everybody good? All right. Before I click, are you okay with, or do you understand where that came from?
You just plugged it.
I just plugged it in here, right? Squared it.
Why does?
The 4's canceled because 2 squared is 4. 4's canceled. Square root of 16 minus y squared. Squared is 16 minus y squared
The triangle?
from the formula. Yep. Area of any equilateral triangle is s squared. Squared is 3/4. Okay. So I did choose to move the square root of 3 out in front. You didn't have to. You could have distributed it, whatever. And I went from -4 to 4, but again, I could have gone from 0 to 4 and doubled it, or -4 to 0. A lot of times it's not bad to double it because plugging 0 into integrals is a lot easier sometimes, not always. Plug and chug, and I get 147.802. And again, that's not really that important for us right now. What's more important is that you can set these things up. I'm assuming that you can do basic integrals here. Just as a helpful hint, don't forget those parentheses when you plug in the -4. Sid?
Can you go to the back page?
This guy?
Yeah, how did you get 2 square root of 16 minus y squared?
It's the base of the shape, which is the same thing as the side of the triangle. Okay.
So when you get x, how do you know where x is? Is it just like where?
It's wherever you want.
Just a
Yeah,
point?
I just happened to throw this representative rectangle in here. I could have put it up here. I could have put it down here. I could have put it closer, further. It doesn't matter. Just like when we're doing representative rectangles for shells and discs and washers, you put it wherever you want.
So is x then the x coordinate of the point where the rectangle?
Yeah, in that particular case, the x coordinate of this,
Okay.
because it's a horizontal rectangle, most of our stuff would be in terms of y.
Are we always gonna have to double it?
No. Not every figure isn't going to be symmetrical.
So if it wasn't symmetrical,
You can't double it. It's got to be symmetrical in order to double it.
we have to figure out like.
Are you talking about doubling this, or are you talking about when I set up the integral of doubling it? That, yeah, this is going to have to be doubled. Because we find that distance first
Yeah.
from the y-axis, and then double it to get the entire distance. Okay? Da, 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 da. We're done. Okay? It's a cross-section of the Millennium Falcon. In case you didn't know. Okay, good. You got 2 things tonight. There are only 3 problems on this stuff, which I believe, in fact, I'm sure, is day 102.
It says on the calendar, day 105.
I know.